I want to welcome everyone to the 22nd Annual Ronald A. Mitsch 3M Lecture in Chemistry at Hamline University. Our special guest is Professor Geraldine Richmond from the University of Oregon. The title of our lecture is Surf, Sink, or Swim. I'm Nick Schlatter, and I am the current Chemistry Department Chair at Hamline University. I will be the host for this event and will provide some background information and introductions for Hamline's president, Chemistry Department, a student Mitsch Scholar, and finally for tonight's speaker. I will also be moderating the live question and answer session directly after the presentation. First, it is important to thank Ron Mitsch and 3M for their support. For Hamline students and faculty, the 3M Mitsch Fund has provided significant support for student scholarships and summer research stipends that have been instrumental in our goal to give as many of our students as possible a research experience. The Mitsch Fund has also allowed us to maintain our research instrumentation. 3M and Ron Mitsch's generosity have been incredibly fruitful, with many of our supported students going on in science careers. Thank you, 3M and Ron. At this point, I would like to introduce Hamline's President Miller to speak about the 3M Ronald A. Mitsch Fund, which makes today possible. President Miller, the floor is yours.
Thank you, Nick. I'm pleased to welcome you here today for the 22nd Annual 3M Ronald A. Mitsch Lecture in Chemistry. We're gathering again virtually for this signature event, offered to students, the Hamline family, and the state's scientific community. Hamline is proud to host many noteworthy lectures on its campus in a variety of disciplines. Hamline University's mission statement, values, and vision are put into practice every day. We are driven to create a diverse and collaborative community of learners dedicated to the development of students' knowledge, values, and skills, leading to successful lives of leadership, scholarship, and service. The 3M Ronald A. Mitsch Lecture in Chemistry exemplifies the values Hamline University promotes. We are pleased today to have Dr. Jerry Richmond as our speaker. She is a Presidential Chair of Science and Professor of Chemistry at the University of Oregon. Currently, she serves as the Undersecretary for Science and Innovation at the Department of Energy in Washington, D.C. Dr. Richmond's dedication to her field, her students, and service is remarkable. We'll hear more about her when Professor Nick Schlatter introduces her. Dr. Ron Mitsch is a graduate of Hamline University, class of 1956. He joined 3M as a research scientist 4 years later, garnering 19 patents for his work there. When he retired in 1998, the 3M Foundation established an endowed fund to recognize and appreciate Ron Mitsch's outstanding leadership and service to the 3M company. That gift was matched by Ron and his wife, Marilyn. Together with Hamline University, they created the 3M Ronald A. Mitsch Endowed Fund in Chemistry. Their combined generosity supports this lecture, plus several scholarships and collaborative research grants. On behalf of Hamline University, I want to extend our thanks to Ron and Marilyn Mitsch for their generosity. It allows students opportunities to do exceptional scholarly work at Hamline and to prepare for careers of service and leadership. Thank you. It is now my pleasure to hand things back to Dr. Nicholas Schlatter, Chair of the Hamline University Chemistry Department.
Now I'd like to briefly say a few words about Hamline's Chemistry Department. Our Chemistry Department is an American Chemical Society certified chemistry department, and we strive to prepare students to be ready for careers in chemistry, but also in other fields that find technical backgrounds important. Our students are prepared for a wide variety of things, whether getting into graduate programs, medical fields, law, business, or something completely different. We have many students that have gone on to highly successful careers. While at Hamlin, we provide our students with research experiences that are authentic and often lead to presenting at regional and national levels, and occasionally contributing to peer-reviewed publications. Our faculty run summer research programs in a variety of areas, such as organic synthesis, medicinal, biochemical, polymer, plasma matter interactions, nanotechnology, forensics, inorganic materials, and many more. Who are these faculty and what are their interests? I am Professor Nick Schlatter, and I am a physical chemist and the current chemistry department chair. My research is focused on nanotechnology, and one of my current projects involves nanotechnology and spectroscopy to detect biomarkers. Professor John Matichek is our inorganic chemist with biochemistry interest. His interest involves electrochemistry and applications of NMR. Professor Rita Majorly is one of our organic chemists and has interest in synthesis with a medicinal chemistry twist. Visiting Professor Urvashi Gangal is a physical chemist with interest in applications of plasma in chemistry and chemical education. Visiting Professor Mark Schulten is an organic chemist with interest in polymer synthesis with applications in biodegradable polymers. I would also like to acknowledge our past lab coordinator, Marina Gorina, who has held the internal workings of the department together throughout all the challenges of recent years. I would also like to welcome our new lab coordinator, Becky Capon, who has big shoes to fill, but I'm confident she will excel in doing so. Our current Mitsch Scholarship holders are Kay Dolan, Clemisha Hughes-Barbie, Aubrey Shavara, Kaylee Stevens, and Thomas Residlo. I think we should applaud them. We will now hear from one of the students, Aubrey Shavara, about their Hamlin experience and research.
Hello, my name is Aubrey Chavaria. I'm a junior class of 2023. I am majoring in biochemistry with a minor in public health here at Hamlin University. I chose Hamlin for the opportunity to further my education in a great environment with professors who truly care about me and my education, and the ability to complete research very early on in my career here, as well as continue my passion and love for athletics, being part of the swim and dive team here at Hamlin. I'm studying biochemistry and public health to further my passion and my goal in life to attend medical school and become a doctor. I chose these two paths to get to the final destination as I truly love biology and chemistry, and I love the junction of where they meet and studying how life works around us, not just in one aspect but in both, and how they combine to what the world we see is today. With the chemistry department, I was able to become close with my professors and work closely with them, leading to me doing summer research in the summer of 2021 with Dr. Rita Majorly doing synthesis of costumegamide analogs, which was basically a research project on hard organic synthesis and applying all my knowledge from organic chemistry to create these analogs of this larger molecule. This really proved my love for science and made me discover why I do this every day. The Mitsch Scholarship has not only helped me, but has also helped other students and will help future students here at the Hamlin Chemistry Department continue their love for chemistry and for science here at the collegiate level at Hamlin, but also be able to do that and afford doing that with the help of this scholarship. So we thank you for your continued support of the Hamlin Chemistry Department and the future and current students of it.
Thank you, Aubrey. It is time now to give you some background on tonight's speaker. Professor Geraldine Richmond comes to us from the University of Oregon, which is only part of the story, as you shall see. Professor Richmond has an extensive list of awards. Perhaps limiting it to the major name awards will give you an idea of some of the recognition she has achieved. The Linus Pauling Medal, the Priestley Medal, the National Medal of Science, the Davidson Germer Prize, the Hildebrand Award, the Council on Chemical Research Diversity Award, and the Presidential Young Investigator Award. Jerry is also a member or fellow in the National Academy of Sciences, American Chemical Society, American Physical Society, American Association for the Advancement of Science, Society of Applied Spectroscopy, and American Academy of Arts and Sciences, among others. In addition to being the Presidential Chair in Science and Professor of Chemistry at the University of Oregon, Professor Richmond is the Undersecretary of Science and Energy at the Department of Energy, DOE. In this role, she oversees the basic research of the Office of Science, the Applied R&D programs, and the DOE National Laboratories. A native of Kansas, she received her undergraduate degree in chemistry from Kansas State University and her PhD in physical chemistry from the University of California, Berkeley, with George Pimentel. Her first faculty academic appointment was at Bryn Mawr College as an assistant professor from 1980 to 1985, followed by her appointment to the faculty at the University of Oregon. The U of O has been her home ever since. Dr. Jerry Richmond has done a lot. Over 230 scientific publications, over 150 invited presentations, and over 200 research seminars. In addition, there are at least 20 pages of her CV listing public presentations and workshops given around the world. In addition, Professor Richmond has held numerous leadership roles in the national and international scientific arena throughout her career. She is currently serving on the National Science Board and is Secretary of the American Academy of Arts and Sciences. She has recently served as U.S. State Department Science Envoy to the Southeast Asian Lower Mekong River countries of Thailand, Myanmar, Cambodia, Vietnam, and Laos. She was the recent president of the American Association for the Advancement of Science, AAAS, and recent president of Sigma Xi, the Scientific Research Honor Society. There are many other leadership positions in her past as well. A strong advocate throughout her career for diversity in the scientific workforce, Jerry is the founding and current director of COACH, the Committee on the Advancement of Women Chemists, a grassroots organization formed in 1998 that has helped in the career advancement of over 20,000 women scientists and engineers in the U.S. and in over 20 developing countries in Africa, Asia, the Middle East, and Latin America. I originally met Jerry when she was at Bryn Mawr College and gave a presentation at AT&T Bell Laboratories in Murray Hill, New Jersey in February of 1985. I remember being impressed with her energy then and the fact that she was doing great research at a small school. It was no surprise to me that a Division I school made her an offer. In case one doesn't know, this is an exceedingly rare career path. In the years since, Jerry's energy has not abated. The 72 pages of her CV are a testament to this energy. We are honored to have her with us today. With that, I would like to give the floor to Jerry for her talk, Surf, Sink, or Swim, Understanding Environmentally Important Processes at Water Surfaces.
Good evening, everyone. I am so honored to be able to give this Mitsch lecture at Hamline University, even if the first part is just virtually. What I want to tell you all about this evening has to do with some studies that we've been doing over the years, having to do with absorption at water surfaces, hence the title Surf, Sink, or Swim. We're trying to understand really what happens when molecules get next to a water surface, how it changes the water, and how it changes the molecules that go into the surface. So that's the main focus of it. But first, what we need to do is focus on water. And water is a pretty special little molecule. It's got 3 little atoms, hydrogen, oxygen, and another hydrogen. Sort of looks a little like Mickey Mouse, but it's very important. In fact, it's very special being a triatomic molecule that has some important properties that we still are trying to understand, certainly on a theoretical level. So this water molecule is important because it is basically the essence of life on this planet. not just because we need to drink it, but because it just keeps our whole environment safe, as I'll talk about, and secure. But, you know, when water is by itself in the air, it's very much an extrovert. It doesn't connect with other water molecules. It's just dancing around by itself. However, when it's with other water molecules, it is quite the extrovert, very gregarious, bouncing around, changing partners all over the place, dancing around and connecting with other water molecules through what we call a hydrogen bond. And this makes these properties of water that we see every day really have to do by water as it evaporates from our skin. And that really controls the temperature of our bodies. And that is also because of the fact that these hydrogen bonding interactions cause it to absorb a tremendous amount of heat before the temperature of the water itself rises. So water plays just an incredibly important role in our bodies, but also in controlling the temperature on Earth, which is why it seems a bit cooler when you're near a lake or an ocean. But also knows, you certainly know that it expands when it freezes. It can, because it expands, of course, it can break pipes and even cause water to break up rocks. And it also, because of its lower density, it will float on top of water relative to what you think about many other things is actually becoming more dense and then falling to the bottom of the liquid that it's frozen into. So that means that it really isolates the water that's below it, as you know, in your area of the country, where you can then do things like ice fishing and because the fish are still alive below, because that ice layer above really protects it. So again, that's also very unique for this little triatomic water molecule. But it also has an incredibly high surface tension. And what does that mean? That means that that top layer of water is very different than what's underneath it. And that's why leaves can float on top of water, and also bugs can crawl around on top of water. And equally important is the fact that this high surface tension contributes to capillary action, which allows water to go from the very bottom of the tree all the way to the top to nourish the leaves on the very top branches. And it's really because of that very unique high surface tension, that layer on top that's different than what's below, is what makes it have such special properties. Now, from our perspective, we really want to understand the surface tension and how molecules bond to each other at the surface of water. You'd think that would have been figured out by now, but it still is a puzzle. And the reason that's important from your everyday life is because everything that goes in or out of water must go through the surface, that top layer that has the surface tension there. So even water coming out of pipes, it's the water next to the metal or next to the whatever the plastic is that it's running through. It is in contact, and anything that comes from those pipes has to go through the surface of water in order to get inside the bulk water. It's also important for atmospheric chemistry because of the fact that our clouds are made of a lot of water. Now, we used to think that most of the chemistry in the atmosphere occurred because gas molecules would bounce off of one another, back and forth. But in actual fact, and react, but in actual fact, we know now that a large portion of the chemistry that happens in our atmosphere actually happens in these clouds of water droplets, we call aerosols. These water droplets then, where whatever is in the atmosphere, a gas, for example, has to get through that droplet in order to then do the chemistry that's up in our clouds. And in fact, our clouds of aerosols are actually little chemical factories in those aerosols. So it's also important for issues of environmental remediation to be able to understand the surface of water. For example, much of the work that we've done in our laboratory over the years is related to an environmental remediation where you have oil on water. And that oil on water is our concern is to be able to get rid of the oil in a very safe way. And so understanding the interactions between oil and water is very important. I'm going to focus today, though, on atmospheric chemistry and tell you a bit of a story with regards to what we've learned about the chemistry that happens in the atmosphere. So first of all, let's talk about how you measure the properties at the very top layer of the surface, because it's extraordinarily challenging. And I'll explain to you why. The surface of water, that surface layer that we want to understand in terms of the surface tension, is extraordinarily thin, on the order of what we determine to be somewhere around 10 angstroms. That's tiny, tiny, tiny. And so whatever probe you're using to probe that very surface layer has to be extremely sensitive on that dimension. So you can't use conventional methods to do that. But that's where we've got to understand what's happening just at the very, very top layer. So we have to get a little fancy with the way that we make these measurements. So you can't use like a regular light bulb that reflects off or just a single laser beam that reflects off. We have to get a little fancier than that. But before I tell you about the laser experiments, there's also, in addition to the laser experiments that we also do something that's very important, and it's called surface tension measurements, related to surface tension, of course. And it basically is a measurement of the force that the water molecules have within each other that makes it harder for you to, for example, take as I have here, have a little piece of metal. This is actually an oil-water interface, but think of this as air next to water. And what you do then is you pull that little metal piece across that interface, and there's a force on that plate that basically is the way we measure surface tension. So you're pulling that string up, and the force as it changes as you go through the interface from air to water or oil to water gives you a measurement of what we call the surface tension. Now, this is a very old method based on a very old principle, but I love sharing this story because I think it certainly relates to our students here that are in the audience. No, it's a very precious story about how the first surface tension measurements were done. It's really remarkable. And it goes back to a woman called Agnes Peckles. She was in her late teens in Austria. And she was a caregiver for her parents who were ill at that time as they were aging. And so she got very curious about the fact that when she would wash dishes to take care of them, that she noticed that the soap had different behavior with the dishes, depending on how much soap you had there or the different kinds of soap that you're using. Now, today, we know that the surface tension of water can be significantly lowered if you add soap there. And that's why soap works to get oil off of your skin or do any kind of cleaning, because it lowers the surface tension of water, making things more easily to move about. Well, they didn't know anything about that in the 1850s, 1860s. And what Agnes did, or a little bit later maybe, but certainly the 19th century, she was very curious that what she was observing with this change in surface tension. So, but she wasn't able to go to a university at that time, being a female, but her brother was. And he was going to university and he was studying physics, and he was bringing home his physics textbooks and would show how some articles in that textbook were taking data. And so she thought, well, maybe I'll just take some data on what I'm observing with soap and cleaning these dishes. So her idea, which I have depicted here, is she took a button and a string. And what she was doing then with her water and her and air with soap there, she was then basically doing the kind of experiment we're doing today. I'm not quite sure how she measured how much she would tug on it, but then she was taking data to be able to say, well, look, when I have this much soap here and I'm tugging on the string, there's different kinds of behavior. And so she took that on and filled a notebook full of the kind of data that she was measuring, very curious about it. She just wondered if there was anybody else in the world that knew anything about this. So she went to her brother's journals that he was bringing home. And she looked inside and she noticed there was this guy named Rayleigh who had just published a work on the surface of water. And he seemed to be talking about things that were very similar to what she was doing. And so she wrote to him and she said, I've been doing these kinds of experiments. You know, for a 17 or 18-year-old, this is pretty bold. And she told him what she'd been doing with her experiments. And she said, I'm sending you my data because I just want to share it with you so you can see what I've been doing and see if it makes any sense to you, use it in any way that might be helpful to you in understanding the kind of work that you're doing. Because I did read about it in a journal that my brother brought home. So fast forward a few months and about a year, and sure enough, Lord Rayleigh did appreciate it. And in fact, he incorporated it into a paper that he then had her as a co-author. And they kept in touch. And of course, imagine, because Lord Rayleigh then became very famous for what he was doing. And he, of course, won the Nobel Prize. And Agnes was a little bit of a contributor to that. She went on then to be able to go to university or sort of slip her through in some way. She was able to go there, but she couldn't really continue much with her scientific career because she needed to take care of her elderly parents. But I think what this story shows you is that curiosity can be extraordinarily powerful. And one should be very bold in thinking about the importance of your curiosity as you try to solve problems, no matter how simple or difficult they are. So anyway, we use these surface tension measurements to tell us what happens then when we put, for example, different atmospheric pollutants on the water surface, or for many of our experiments, put oil on a water surface. It gives us a lot of information. But what it doesn't give us is anything having to do with the actual molecular properties of that surface. And that's why we have to go to laser experiments. So in these experiments, what we do is we could just shine a single laser beam on the surface, but in actual fact, just using a single laser beam will actually, and looking at how much light is absorbed as the light beam comes off the surface, that will actually be probing about 1,000 angstroms, 100 times deeper than what we want. So we'd be measuring a lot of water molecules and their behavior in the bulk rather than just on the very, very top layer. And so what we have to do to just get at that very, very top layer is to use a visible laser beam and a tunable infrared beam. And I'll explain to you in a minute about the importance of the infrared beam. And we reflect those on the surface of water. And of course, the IR beam and the visible beam are going to come off really bright. But there's a very, very weak beam that comes off that is actually the summation of the infrared and the visible beam. And that's what we detect. We have to have very special detectors to do that, to be able to measure that tiny little beam that comes off. And why that is important is because that light can only be generated where what's above look different than what's below. So if you're at the very top layer, the air looks different than the water on an atomic level. But if you go 10 or 12 angstroms, 20 angstroms into the water, then what's above looks the same as below. And so it wouldn't generate that kind of light. And so that's the kind of light that we're after, because it's going to tell us something about what the water molecules are doing at the very, very top layer. So let's back up just a little bit. Some of you, some of the students may have had this in some of your courses having to do with what we call vibrational spectroscopy. Those of you that haven't, just hang in there. You'll still be able to follow. Now, our molecules that we have all around us, they vibrate. They're very active, and water is particularly active in these hydrogen-oxygen or carbon-hydrogen bonds. Going back and forth, and they do go kind of different directions too. And if you and the reason that they absorb infrared heat in order to do this. So they absorb a lot of infrared light that goes in, and the color of that infrared light that it absorbs, or it is resonant, we say, it can tell us a lot about whether water is by itself as an extrovert, whether water is bonded to another water molecule, or 3 water molecules, or 4 water molecules, just by the color of light that is absorbed by water. And that's why we use a tunable infrared beam with our experiments, because when that tunable infrared beam is resonant with one of these modes in water, which are quite distinct, then that will then generate this weak light that's given off will be bolstered, and it will get stronger. So if your infrared beam isn't resonant with that OH stretch, it will just be a weak beam. But once it gets really going with those OH modes, then it'll give up a much stronger beam. And so we can watch the signal go up and down as you then reach a resonance. So we can figure out from that weak signal that's given off whether water is bonded to 1, 2, 3, or 4 water molecules, but we also can measure the orientation of the water. So for example, does the water straddle the interface with one OH going down and one OH going up? Or might it be in the plane of the interface? Or how is it actually oriented? And that's really important, as you'll see in the studies I'm going to tell you about. So this is just showing different water molecules there, 1, 2, 3, 4, that we can measure with a frequency. So those measurements are really great, but they also have some weaknesses. And so what we do, and I'll give you an example of that. So what we do then is to also be able to do molecular dynamic simulations, which are simulations, computer simulations, along with density functional theory, to determine more about those interfacial water molecules that we didn't have before. Okay, so with that as background, now what we want to do is see if we can understand what that surface of water looks like on a molecular scale. So we're going to look to see how water molecules bond to one another and how they behave. As I said, the surface tension is very high. So does that mean that the bonding, 1, 2, 3, 4 water molecules bonded together at that surface, is that different than in the bulk? Because we know in the bulk that it tends to be water that's bonded to 3 other or 4 other water molecules. And we know in the gas phase, it's just simply monatomic. Okay, so this now is what I was alluding to before, which is a vibrational spectrum, in this case of the air-water interface. We have the intensity. That intensity along the axis is the intensity of the weak beam that's coming out. And then we're tuning that infrared light and and looking to see when the infrared beam is resonant with water molecules at the top layer. And that resonance then, of course, gives us the stronger signal. Now, you'll see a big, broad blob and also a very sharp peak. And that very sharp peak is curiously quite different than what you might expect from water in bulk. In fact, you don't see this in water in bulk. And what it tells us is that there are water molecules at the surface where one of the OHs goes up into the air and the other goes into the water. So about 25, so when you look down at your water glass, the water that's there, if you could look on a molecular level, you would see about 25% of the water molecules have this OH sticking up there, and then the other OH going into the water phase. So that in itself is unique, having to do with water. Now, this spectrum is actually showing the weakest interaction with other water molecules is this free OH. And then as you go further down the spectrum to 3,400, 3,000, 2,800, you find stronger and stronger bonding. So when you get in the region where you have that very broad peak, those are water molecules that are trigonally, quadruply bonded to other water molecules, a lot like water or ice. And so from that kind of information that we get from the spectrum and taking a lot of different spectrum, doing what we call isotopic dilution studies, we've been able to generate a pretty good picture of what the water surface is, along with the molecular dynamics simulations. And so this is now what we've learned about water at the surface of that air-water interface. At the very top layer, you have a low density of water molecules. They've got this OH sticking up into the air. And then you go about 3 to 5 angstroms down, and these dimensions we get from our molecular dynamics simulations, but you see it also in the spectrum. You see water molecules that are largely in the plane of the interface, a little tilted about 5 degrees off axis, but they are a little bit stronger bonded to each other. rather than that very top layer, stronger bonding, but they have a net orientation. Once you get down to about 10 angstroms, so 4 or 5 water molecules into the solution, then you get bulk water, which has completely random orientation. And so we're not going to pick up those water molecules because we can't pick things up that are completely random because things don't look different from different angles. And so we have to have, in order for us to see what these water molecules, they not only have to be near in the surface region, but that surface region is defined by something that has a net orientation in one direction or the other. And so we know we get to bulk water because that's when we stop seeing the signal. Okay, so that's what we're seeing at the water surface. And now what we want to do is to be able to talk about the environmental side of this. So as I said, what we're very interested in understanding is what happens when different environmental species get to the surface of water. How does it change that bonding interaction between water molecules? And also how it enters and reacts once it goes into the liquid. So as I mentioned, the water surface is really an entryway in any case for anything that water's in contact with, but it's particularly important for atmospheric pollutants, whether it be in lakes, clouds, or oceans. So being able to understand what happens when, even in the laboratory, when different gases or pollutants get next to a water surface is what's really interesting to us and important to us. Because even in the area of climate change, if we're going to understand the chemistry that's going on in the atmosphere, the weather that's going on in the atmosphere, what we need to be able to do is to be able to understand first what happens when these pollutants interact with the water surface, or even how the temperature modifies the surface of water, which you can imagine is important as we try to understand issues of climate change. It's also in our oil water studies, it's also important for us to be able to understand what happens to the surface properties of water as oil becomes next to them. Okay, so what I'm going to do is I'm going to focus on, focus of this study is on SO2. And in this study, what we're doing is we've chosen to look at sulfur dioxide because sulfur dioxide is very prevalent in our atmosphere. And we also consider it to be a pollutant. So where does it come from? Well, it comes from sulfur dioxide gas comes from different ways. But it turns into being a precursor for acid rain. So once sulfur dioxide gets into the air, gets into clouds, it oxidizes and then can form acid rain. I'll say a little bit more about that. But we can get it, for example, from volcanoes give it off in my side of the country. In Oregon, when there's a volcano that goes off, it tends to give off sulfur SO2, and that converts into sulfur dioxide. So SO2 also goes into the atmosphere, just biogenics. But it also comes heavily from what we call dirty coal. And dirty coal, it has a lot of sulfur in it. And so when the coal is burned, it puts out sulfur dioxide that goes on in the sulfur cycle to form sulfuric acid. In all these cases, the SO2 that's given off goes into the clouds and produces H2SO4. But as you can understand, as you can appreciate then, it's important to understand what happens when SO2 gets to the surface of the clouds or surface of water. How does it form sulfuric acid? What behavior does it have at the surface of water? So that's what we've been really curious about because it's one of the first studies that have been able to tell us something about this. Okay, so we know is that the major source of sulfuric acid in the air is from uptake of SO2 into clouds and fogs. And then it's oxidized with H2O2 or O3 in the liquid phase to form sulfuric acid. And some recent studies by Barbara Finlayson Pitts that not doing our technique, but in other beautiful studies, suggested that there might be some kind of surface reaction that SO2 would go to the interface, it would react with water at the surface at the interface to form the precursors for sulfuric acid. But they didn't have a way of proving this. And so we decided, because our technique was so sensitive to those very top layer of water molecules, that maybe we could just get information about this by probing the surface of water to see how that spectrum I showed you before changed when you put SO2 on the surface. Okay, so what our question or our hypothesis, what role does a water surface play in gaseous uptake? And so now I thought it only appropriate, since this is the evening, that you should take a multiple choice quiz. So now I'm going to challenge you and with giving you some data. And I'm going to give you 3 choices to figure out what happens when SO2 gets near a water surface. Okay, here are your 3 options. One is when SO2 gets near the surface, does the water just open up? Does the water expand and let the SO2 come in? That would be the doorman. The next one would be a barrier, and that is once the SO2 gets near the surface, it just bounces right off. It just bounces right off. And the third one is the temptress. And the temptress is there to help pull the SO2 into the surface so then it can react as it goes into the liquid. Okay, doorman, barrier, or temptress. Okay, here we go. So let's see what the data tells us. First of all, I go back to the spectrum that I had with the pure water surface. And now I've got water molecules here in the picture. And let's think about now what happens then as the SO2 gets to the surface. Well, during the experiment, which doesn't absorb any of the SO2 doesn't absorb any of the infrared. What you see though that happens is that free OH gets broader. And also there's a stronger increase in where we have the very strong hydrogen bonding, which is in the lower region of the spectrum. That tends to increase. So something's going on at that free OH that's there. So clearly some type of complex surface forms. Then also this region, that's the broader region, that it really corresponds to SO2 going into the surface and creating ions, which then change the structure of water. Okay, so is it reversible? Well, if we blow the SO2 flowing on the surface and then we take the SO2 away, let's see what happens when the SO2 is taken away. And what we find is when the SO2 is taken away, that actually the only change that you see is these ions that you create, which shows that the SO2 is actually going into the surface and then still creating ions that are there. So we know it's going into the surface, but if the SO2 isn't there, you don't see this very top layer of bonding. So then we wanted to see if the surface complex is temperature dependent. So we did a series of experiments where we got the water colder and colder and colder to see how that would affect SO2 absorbing. Because again, the clouds are quite cold and we're doing this in our laboratory at room temperature. And so what we have is it gets colder and colder. You see that actually the more complexation happens at that free OH, the peak gets broader and broader. And so we did experiments then to try to fit spectra to figure out what was going on. And what we found out was we start out with the free OH, that's the single bond straight out. And then we, as we go colder and we do the fitting, we find that the SO2 bond is bound to the OH, but it's shifted. So we believe that the blue peak has to do with a bond that's shifted, and then you've still got some free OHs, which are the red peaks. And then as you get colder and colder, you eventually end up with the dominant species being every single OH is bound to SO2 in some kind of interaction, But what does that interaction really look like? Because we have a very fluid surface. It's not as if it's frozen and the OHs are always there. It's very fluid and it's moving around. And what we're measuring is actually the average of the bonding interactions. And so the experimental results could only tell us so much about what we're seeing. So we know it's bound, we know that it goes into the water, but what can our computational studies fill in with regards to the details? So how does SO2 approach and bond to the surface, and what's the molecular structure of the complex? So this is now a picture of SO2 next to water. And we've got water, I've got just a few of those highlighted. The other red and white are all other water molecules too, the same size. But in this case, we've got SO2 that's coming towards the water surface. It's going to get pulled down towards the water surface. And this is a little video of what we believe is happening as a simulation. And I want you to keep an eye on this SO2. It's kind of wobbling around out there because that's going to give you the answer to the multiple choice quiz. Okay, so it's got a little string on it to pull it down, very weak one. It's coming lower. Look what's happening to those water molecules. Look what's happening to those water molecules. Okay, all right. And then eventually the SO2 goes into the water, and then it becomes too hard for us to calculate beyond that. But you saw that, you see what's going on there. Okay. So what does the surface complex look like? Now we take these simulations and we look at them and we do a histogram of the different kinds of complexes that if your eye could pick up all those in snapshots that we see. And what we've got here is then a histogram at 2 different temperatures, and the room temperature and then the close to 0 degrees. And what you see is that there are complexes that are more complex than just a free OH sitting on the with one SO2, but actually there's other configurations there. They're sort of gas phase-like. And so what you see usually is there's at least 4 water SO2 molecules bound together. That's the most prominent species. And they tend, in that case, the water certainly tends to bond more likely to the sulfur and the hydrogen in ways that are complex with regards to the electronic structure. Okay, so now we're ready for answering that quiz. So what role does a water surface play in gaseous uptake? And now I'm going to have to maybe have Nick apply the quiz, and while I'm just here, and you can do some voting. So let me just summarize what we've just seen. Get ready to raise your hand, whether it's one or the other. We've got water molecules. We had SO2 go down. The water molecules now change their orientation, and they start to surround the SO2. And they form different complexes that are most prevalent. So the question becomes, doorman, barrier, or temptress? So I'll let the vote happen. How many think it's a doorman? Oh, come on, be bold. Raise your hand. How many think it's a barrier? How many think it's a temptress? All right, are you ready? Here's the answer. It's the temptress. So all of you that thought it was the temptress, you're right. You're right. So now, because those water molecules went up and got SO2. Now, I just want you to know, I spent a lot of my career on women's issues, and certainly a feminist. And so for me to put a picture like this on this as the temptress certainly was a struggle. So just to show that I'm an equal opportunity employer, I looked on the web to see what a male temptress looks like. Anyone guess? Okay, this is, a male temptress is actually considered the devil. So I didn't think the devil was a good representation for something that would pull SO2 in. But I have to say, so I looked for a picture, you know, I saw the devil there, didn't look quite right. But then I started thinking, so I just happened to have been with this guy, this husband I've had been hanging around with for over 40 years now. And I thought, you know, he pulled me in, and what picture would I give of him? And I thought that this was probably the best representation of him, the kind of temptress that would certainly pull me in as a guy. So anyway, I hope you learned something from that having to do with what happens in this really model system, but the only experiment that's been done of this type having to do with a gaseous molecule absorbing at a water surface. So interestingly enough, we went to see if the same thing would happen with carbon dioxide. So carbon dioxide, you know, is in our air, and is certainly important now as we try to understand climate change. And then we did the same kind of spectrum, which we have in the plot here. And no matter what happened with the CO2, we never got that free OH to change its position or change its structure at all. So we believe that the CO2 just dives right into the water. And you certainly do that experiment at home, because you knowing that CO2 goes into your water, because you put your glass of water out at night and you drink it before you go to bed, and then you drink it in the morning and it tastes different. And of course, that's due to the fact that the CO2 absorbs into the water and it makes a little bit of acetic acid, a little vinegarish like. And that's the kind of tinge that you're picking up when you drink it in the water. But anyway, very, very different. But also CO2 and SO2 have very different thermodynamics when they absorb with water. So maybe that's not so surprising. So anyway, that's my story I wanted to share with you tonight, having to do with what we're learning about understanding environmentally important processes at water surface. We've gone on to do things having to do with nitric acid, different molecules at the surface that actually could capture carbon dioxide from the atmosphere, and a lot of work having to do with oil on a water surface. So before I end, I promised that I would say a little bit about my own career and career trajectory, and also what I'm doing now. But first, let me give thanks to the many graduate students that were involved in this project around water. And the three here would be Eric Chamet, and I also have to say who's gone on to be a computer scientist, very much so. And then also Teresa and Emma in their studies too. So, and all done. This is actually Stephanie. Emma's in the picture, but Stephanie and also Teresa Tarbuck, who funded by NSF at the University of Oregon. And while, but I've taken a little bit of a jog now with regards to my career. So let me go back and do a little bit of reflections on where I am today. So here's the one slide summary of my life. You would have put this all on one slide. I grew up in Kansas, sort of like Dorothy, on a farm initially, and then got my undergraduate degree at Kansas State, then went on to do a PhD at University of California at Berkeley, working for a guy named George Pimentel. It was a big shift from Kansas to Berkeley, needless to say. Then after receiving my PhD, I then went to work at a small college on the East Coast, Bryn Mawr College, which is a women's college. And this is a picture of myself with my students at that time, who I still stay in contact with, I'm delighted to say, and had a wonderful time there at Bryn Mawr College. And I had a research program there as well as teaching, but the research then got more important than I anticipated. And so I wanted to go to an institution where I could do more research in addition to the teaching. And so that brought me to the University of Oregon many years ago, where I then have been fortunate to have many wonderful graduate students. But in this whole process, particularly at the University of Oregon, things happen in your life. My husband I met at Cal Berkeley, that I referred to as my temptress, still with him. And so we had started to have kids grow up. Then you start throwing in a bit of a little farm around our house, and very happy doing that. And then so it sort of takes me back to Kansas. But then in the process, I've been so fortunate to have this fabulous group of students and postdocs in my laboratory over the years that I am eternally grateful to and love every single one of them. And we actually have a lot of traditions in our laboratory, whether it be dressing up for Halloween, or also another one, whereas once you do something phenomenal, we celebrate by throwing a pie in your face. And so we have a pieing tradition, which is one of the pictures that is here. And I have been pied my share of times also. So, but then as this has gone on, there's been a change in running a research group. Then I was contacted by the Biden administration to consider serving as the position I'm in now, and to work on climate change. And as much as I love my students and I love what we're doing, just the chance to work in the Biden administration to work on climate change in the position that I hold was hard to turn down. So my laboratory is still operating in a much lower mode with other people, smaller mode with other people involved while I'm in Washington. So, but before that, before I took this position, I also, I think a lot of students don't understand that when you go into science, it's not just working in a laboratory, but you get to work in a lot of other countries. And so I started an organization for women scientists in the US, and then that became international. And so in the last 10 years before COVID, it took me to all these different countries to work with different scientists in these countries, both women and men, both in terms of coach, but also for Secretary Kerry, I served as US Science Envoy to the Lower Mekong River countries, which took me more to Southeast Asia, where I got to meet and work with ministers there and trying to develop scientific collaborations. So, that and working on all kinds of issues to help us build stronger collaborations. So all of that international work, as well as our scientific credentials and our diversity efforts that I've been working on all these years, then took me to Washington, DC, where I now live. I have a part-time apartment there, and then get back to Eugene with my husband when I can. But it's a bit of a change. I've been in the position now for 5 months, and I've learned a lot. It's in this position that I'm in. This is a picture of my behind my desk in my office, Under Secretary for Science and Innovation in the Department of Energy. And if you understand org charts, we have of course, the Secretary of Energy, who is phenomenal, Secretary Granholm, and then we have a Deputy Secretary, and then there are 3 undersecretaries. One, and the NNSA Secretary, who's in charge of all the our nuclear weapons and also security. And then we have my office, which oversees all of the science that the Department of Energy funds, including all the funding for the 17 national laboratories that we have around the country. All the basic sciences, the largest budget for physical sciences in the world is in the Office of Science, which I oversee. And then I also oversee the applied science areas, which is several areas having to do very much with taking that basic science and turning it into more applications-oriented work, having to do with everything with having to do now, especially with climate change. And then the third undersecretary, Kathleen Hogan, is now doing a new part of our Department of Energy mission, and that is to take everything to deployment. So we now have a spectrum of going from very basic research to all the way to deployment, with the $61 billion funding that's now come from the infrastructure bill. And so I'm taking care of everything getting up to deployment, and Kathleen takes it from there. I want to say that the person in charge of the nuclear side of it, NNSA, is Jill Ruby. So I hope you recognize that we have the Secretary of Energy, which is female. We have the Deputy Secretary, who is sensitive to female issues, but male. And then the 3 female undersecretaries. The first time my position has been held by a female, but also that all 3 of these are women, and we just are having a great time together, as well as all the teams that we're working with, which actually probably that I work with are at least 50% women working in science policy, but all very good at science. So it's certainly been a change for me, but let me just say a few words about what we're doing, because this is really important especially for all you young folks out there. If you want to get involved in something that really makes a difference in the world, then get involved in science having to do with climate change. And that can be all the way from biology, through chemistry, through physics, through material science, the whole gambit, and also science policy, So the president's climate goals are by 2030 to reduce our net greenhouse gas emissions to 50%. It's 2035, 100% carbon pollution-free electricity, 2050 net zero emissions economy-wide. All of these, there's a lot in all of my portfolio with regards to these issues. I oversee the grid issues related to our electric grid, as well as oversee release of oil, as we just had with the Biden President Biden just releasing the SPR, the oil reserves, as well as having lots and lots and lots having to do with carbon capture. And we're doing this through a new initiative called the Energy Earth Shots, And that's to do science, to really fund hard science that's necessary and urgent. And that's to get the remaining major R&D breakthroughs that we must achieve in the next decade to achieve our climate goals of net zero carbon goals. So we have a hydrogen shot, which is our goal of, and hydrogen is very, very important because it can be used as energy storage. It can also be used as an energy source. And so in this case, $1 to be able to get to, we have metrics that are based on market to be able to create clean hydrogen, $1 per kilogram in a decade. In carbon negative shot, what we're trying to do is to be able to develop new methods so that we can reduce the ambient carbon dioxide that's in the air, to be able to reduce that, and again, with goals. And the third one is really long duration storage so that our batteries storage lasts longer. And that's certainly tied in with very efficient EVs and cars. And so that's my day job now. And I'm really glad that my day job allowed me to be with you this evening. So with that, I want to just be able to say thank you very much for letting me be with you this evening. And I look forward to answering any questions that you have that I might be able to help you with if we can get me to come back on for real. Thank you again. Bye-bye.
I wanted to thank you. It was a wonderful talk. I have to say that water is something I appreciate more and more as I go through the years. I have a number of studies where I just am baffled by what water is doing, and I've followed your work for years, so I like that very much. And your new direction with the energy and the issues we have with climate change, I'm so happy you're doing that and delighted. I will monitor the questions that come in it should show on my screen, chemistry@hamlin.edu. So people have questions, just shoot them out there, email those, and I'll bring them up. Let's see. Oh, so many things. Water, one of the things that I don't know if you've looked at, but those surface layers, they have a lot of entropic behavior. Was that something that was covered in your studies with the molecular dynamics, perhaps? Did you do anything with that?
So,
can you hear me, or?
it's delayed. There's two voices, one delayed from the other.
Oh, weird.
Yeah,
did you close your streaming window?
Close my screen. Yes.
Okay.
Now let me make sure this. Oh, that's the problem. That's the problem. All right, let's try it again.
Okay, so can you hear me now directly?
Yes. Great.
Excellent.
Great.
Okay. Yeah, I was asking a question about whether in your modeling you'd looked at some of the entropy effects with water at that surface layer, because it becomes structured, and that, from the things I've dealt with, that seems to have an impact on it. What did you see?
Well, we didn't do so much of what you're asking. Actually, is a really important question. We didn't do so much with specifically looking at entropy, but the modeling certainly showed that you have certain layers that are very top layers that are very, very well ordered and tightly bonded. But as you go a little bit lower, and you don't have to go much lower, then you really get more of the entropic effects coming in. So the very top layer is not only are there fewer bonds, but they're also very much stronger. So but again, as you go not too much deeper in that first 10 angstroms, then you really get a lot more. Even the second layer, you start to get a lot more entropic effects there.
Okay. Yeah, I looked at this from some water on surfaces, solid surfaces, and that first layer of water would go down in particular surfaces such that it was almost hydrophobic to the next layer of water, which was kind of shocking. And then when you start looking at things with hydrophobic behavior of droplets of water on surfaces, you begin to wonder if they're even interacting at all, because you can make these surfaces extremely hydrophobic.
Yeah, right.
So that's one of the reasons I followed your work for a long time.
Yeah, because of the weak bonding we see between water and certainly a liquid hydrophobic liquid. Yeah, but still very weak.
Right. Let's see. Waiting for some questions to come in, but in the meantime, so you mentioned sort of touring the world, and that seemed very energy intensive. What did you think of that? Did you enjoy that? Were you running clinics everywhere? It seemed like there was so much going on.
Yeah, so a lot of the work was to go into country and a first visit, particularly in Africa and also parts of Asia. The first visit was really to learn the culture, to see if they would have an interest in doing the kind of in learning about how to be more internationally tied in to do science and what the international norms are, and then go back to do workshops with different scientists there to help them, whether it was about publishing or grant proposal writing or getting money or getting fellowships. And so, but it had to be culturally sensitive. So I loved it because I really I'm not very good at sightseeing. What I really like is getting to meet people and getting to understand the things that are interesting to them. And so for me, science was a great opportunity to get to know people, and then from their science, but then you find out some really beautiful personal stories and challenging personal stories too. So it was great to be able to do that. Unfortunately, to scrape together money to be able to do it, and so it was great. But it does take a lot of energy, because these trips were, a couple of days there and then home, or 3 days there and then home. So a lot of travel.
Right. So I have a question. Edwin Ellis writes, "What do you enjoy the most overseeing research? I think in overseeing research projects and their progression." So.
Oh, there's no doubt. For me, it's working with my team, with the students. That's what I enjoy the most, because as you get into a faculty position, it's really the students that are doing a lot of the work. And I love coming up with the ideas, but I like them being a suggestion to the students, and then watching the students kind of struggle through it. But then when they succeed, it's just great. And then when they take hold of it and they go with it, and that's what I really love. And I love doing the science too, but there's a richness that comes with it when you're working with the students.
Okay. Betsy Martinez-Vaz writes, NO and NO2 are common air pollutants.
Uh-huh.
How do they interact with water molecules at the surface? Have you studied this before? Particulate matter, and does interactions of SO2 with particulate matter change its interactions with water molecules? So there's a couple questions there.
Yeah, so let me go back to the NO and NO2. So what we did in these studies was we were looking at nitric acid solutions, and of course NO going into aqueous solution and then oxidizing can form nitric acid. So we know that in aerosols there are high concentration of nitric acid. And what we wanted to do was to see if we could understand what the behavior of nitric acid itself was at the surface of water. So again, it was just in laboratory experiments. We came up with this really interesting result. And that is, as we know, that nitric acid in bulk solution, right, is very, very acidic. It loses its proton very easily. But as it goes to the surface of water, and we can do the spectroscopy of the NO modes of nitric acid, and we also did the DFT and molecular dynamics calculations. And what we found is as the nitric acid approaches the surface of water, the fact that it loses its water shell as it gets closer to the surface, it does not deprotonate. It stays protonated. And so at the surface of water, a nitric acid solution is actually a very weak acid at the very surface layer, while it's just viciously acidic when it's in bulk. And you can imagine that that makes a lot of difference for any type of aerosols, because the reactivity, a lot of the reactivity is believed to be at the surface. It has to get through the surface, but just a very, very weak acid when it's on the surface of water. And then we did a lot of studies having to do with throwing in sulfuric acid and nitric acid and mixing and see what effects of those were. But not so much gaseous going on to a water surface. And also we didn't do any particle studies either. We didn't do any particle studies. So thanks for that question.
Yeah. So, you know, one thing that puzzled me when I think about this is you have these OH bonds sort of sticking up in the air out of the surface, which I wouldn't have predicted. Did that surprise you when you found that?
Yes. But it also, what's also, Nick, surprising to me too is, you know, we're not studying a solid water, right? It's, you know, it's got capillary waves and everything else. And so what you're really doing is looking at these water molecules that on the average have this orientation, whereas otherwise they're moving around the lab. But I think it is very interesting. And what's also interesting to me is, you know, water has to evaporate. So, you know, there has to be some weak, it has to, you know, that's entropy playing its game too. But we could see these guys, which are very weakly bonded, but we could never see a little, you know, free water that you might say right next to the surface that's going up into the atmosphere. We looked really hard for that, but we were never able to see any signature of that.
Okay. So what advice do you have for people who want to get into politics?
Oh, that's an interesting question. It's an interesting question from many directions. So if you want to get into politics and you're a scientist or you have scientific background versus just jumping in, I think, I'm not an expert on what you do to become a politician if you're not a scientist. But let me focus on the science side of it, because there's some really cool things you can do if you like having a science background, but you'd like to take it towards policy. You'd like to take it more in a political realm. And I'm not, there's lots of things you can do with regards to joining professional societies that have activism associated with what you do. What I'm talking more about is to be able to, let me just name a few jobs, to go into the Foreign Service and become an economic analyst and, go from country to country every 3 years, as you get placed different places. And so your scientific and also your economic background plays a big role when you work in these embassies. So going into the Foreign Service. You can also, a lot of the people that I work around now aren't really doing science. They're really developing policies that go along with anything from how you develop policy around drilling, or policy around land use, or policy around renewables, just everything. There's policy associated with all of that. And so there are NGOs that are focusing on issues related to, for example, recycling and things like that. So you could do policy associated with that. And how you get into this, if I can advertise, one great way to do this is after you need to get your PhD in some kind of science, and then you can go to AAAS, the American Association for the Advancement of Science, and you can take on, there's a 2-year science and technology fellowship, and you get a fellowship and you can work in just about any agency you want, federal agency you want in Washington. And those are fabulous positions to learn how to do policy. And then, of course, you can always work on the Hill. You can always work as a staffer. You can contact your local congressman or senator. My son worked in both a senator's office and a congressman's office for a summer each. So, there's just a lot of ways you can use your science if you don't want to stay in the laboratory. And there's a lot of need for scientists that go on to do policy. It's just not one you hear so much about because of the fact that we tend to be in an academic environment. You tend to see those that are doing research or teaching or things like that. But there's a lot of really cool jobs out there that have to do with science policy.
Okay. Yeah, it's kind of related, but as a scientist, and you must be experiencing this maybe tenfold more now, you get these people who don't believe in science. How do you interact with them? How do you convince them that climate issues are real and a variety of other things? I mean, it's I've had a little bit of interactions, but I find it really challenging to kind of convince these people that, hey, we really need to think about change and doing something.
Well, I think that, Nick, it's a very valid point, especially nowadays, because there's so much other information that would counter what we would have as our scientific knowledge. And so I think the best approach is to listen, to ask questions, not in a threatening manner, but really try to understand what causes them not to believe the science. And again, not in an accusatory manner, but then look for shared values. So if you're talking about climate change and they don't believe that the climate is changing, then focus more on, are you concerned about the weather? Even the weather isn't really climate. It's very different. For someone that's a meteorologist versus climatologist. But that aside, and so you can say, well, I have sons of my own. They're in their early 30s, and I worry about them. I worry about whether they will be able to live in a world that's a little warmer or warmer, and what do you think we can do about it? So I think it's a lot listening so you can understand each other before we go lecturing on what's right and what's wrong.
Okay. Yeah, COVID has been kind of a hard one for me with that.
Yeah. No, it's really true. It's really true.
So any advice for people in terms of if the students, we have probably a variety of other students here, but what would you tell them about maybe a particular direction in science? Is there some place they should be looking to more than others? I mean, of course, I'd like to say chemistry, but I'm sure that there must be some areas that would be going forward, and I can guess, but I want to hear your view. Going forward, we're going to be more important in the next 10, 20 years that, might be a real growth area for someone to go into.
Well, I certainly think certainly the problems that we're trying to solve are much more interdisciplinary than, Nick, when you and I were getting out of school. And so when one gets a chemistry degree, it's really important to use the way you think about chemistry to learn other sciences too. And because I believe that this intersection between chemistry and physics and chemistry and biology and chemistry and a lot of different areas will give you a much more powerful background to be able to do that. I think, if you're going to pick up any additional skills, I would certainly pick up skills if you haven't yet in not just computer programming, but even being able to pick up packages that can do modeling. What I mean, Nick knows what I mean by packages, modeling packages and big data packages, because the workforce increasingly is looking for people who can work with data sets and big data sets. And especially with artificial intelligence, big data sets will be a big deal. But you don't have to understand all the all programming skills or all the nuances of handling big data. You want to be able to manage it and be able to get an appreciation for what it means to be working with huge data sets. But again, you don't have to be doing it. You are given some results so that you can analyze it and go further with it, but have an appreciation for what went into that. So I always think picking up a little bit of a little more sort of systems analysis, things like that is good to do. But I can't emphasize that communication skills. I think in science we don't appreciate that enough. And when I was getting out of undergraduate school and graduate school too, you know, I was good at science, but I didn't have a lot of confidence in my science, to be quite honest. And even though I was good at it, but I just didn't. I saw people so much better than me. But what I knew I was really good at was communication, and communication in all ways with people, but also communicating science to people that weren't scientists, and loved doing that. And so I had these two kind of tracks, and I thought they were like this, that, you know, they would grow like this. But in actual fact, as the years have gone on, and it didn't take too many years, I began to realize that they really merging them made me so much better in both of them. And then I had a lot of confidence over here, not so much here, but when I merged them, I had a lot of confidence with them together. So I think, you know, whether it's communication or some other skill set that you have that you know you're really good at, and it may even be in the art world, it may even be in the art or the music world, you know, if you can combine those, it just, you know, it's a way to really zoom off in with your confidence. It can take you in ways you may not have anticipated, and that's certainly been the case for me, because I think my communication skills have an ability to teach well and interact with people, particularly in non-science communities, because you can more easily talk to scientists, has been a real boon for me. So I can't underestimate the communication skills.
Yeah, I think we're doing better on the communication than when I was an undergraduate. We do a lot more work in that area, both written and oral, and I think that helps. We have another question. Urashi Gangle, first great talk. She liked talk.
Oh, thank you.
And how do you apply your research to the current problems you're dealing with? So do you talk about or use any of your research in your current position?
You know, I am to some degree, because even understanding water and issues of water, and that's, you know, studying water has made me more sensitive to the issues of drought and usage of waters and dams, and so in that respect, I have just a deep appreciation that people that are working more on the engineering side don't have. So I think about things a little bit differently. But I think what's been most relevant, even for the work that I do now, is a lot of the work alluding to what Nick had asked about hydrophobic surfaces. The work that we did and continue to do on oil on water, and oil droplets in water. What does the surface look like? You know, all this has to do with, you know, how you come up with a safer way of do oil remediation, and that's even not just oil slicks, but it's also getting oil out of the ground. So a lot of the soaps and surfactants that we use to get oil out of the ground are not very nice, and certainly the dispersants we use to disperse oil in an oil spill are not nice at all. And so, you know, when someone is talking about drilling, or someone is talking about the disasters that come from an oil spill, you know, it gives me a deeper understanding of things that we have to do so that we don't completely screw up the environment, not just by the oil being there, but what we choose to clean it up with. And
sure.
Again, that ties to a lot of the research that we're currently doing today also.
Vashi's got another question, which I was thinking about. This one's pretty good. What type of bond does sulfur make with water, the water molecule? Each water molecule makes 4 hydrogen bonds. How does it bond with sulfur? Is it a type of hydrogen bond? What about carbon?
Well, it's that's really good, because we're trying to figure out why CO2 is so different than SO2. It turns out that the sulfur is a little bit more electronegative than the oxygen, and so it's really lone pair, sort of a positive proton hanging out there, a lone pair. what the picture that I draw, which is really what we learn more with the nitric acid studies, is this is the fact that if you have these lone pairs on sulfur or on oxygen, for example, that once the hydrogen comes up to it, it's not just the hydrogen that interacts, the proton that interacts with it and what it would come up from, but it changes the electronic structure of the water too. These electrons are just, they're just swimming around and they're pulling this direction and pulling that direction. So we like to think that they're localized on this atom and really localized on this atom, but they're actually, moving around. And so we have to think of these clouds as how they move as they come closer to one another. So so I've always wondered, with the carbon dioxide study being linear, is it the linearity of the carbon dioxide why it dives right in, or is it the fact that you have this angle with the SO2? And I never have figured out what the answer to that is. However, what's interesting is that the thermodynamics of SO2 going into water are opposite as to what they are if you go to CO2 if you go into water. And so even the thermodynamics are different for these molecules in water that just have a different structure. So I still ponder that.
More work to do, clearly.
Yeah, more work to do. That's right. When I get done with this gig, that's right.
Oh, let's see. What other thoughts? Do you have anything you'd like to communicate in particular that you haven't covered at this point?
Well, I think, Nick, when we talked this morning with the group, thinking about what my advice would be, going on in a career. And so let me share those three with you, the three of those for those of you that weren't there today, because to me, it's really important to think about where you're going when at your stage. And although I sometimes think I just kind of wandered from one thing to another, I think there's three things that stick out in my mind that have been important, or I've learned. Maybe I didn't do them so well when I was younger, but I've learned. And one thing is that you really want to go in a direction that you value, the things that you value. So you want to think about what you value, and have those values help guide you on what you want to do. So if your values are having to do with the environment or a healthy life, or intellectually wanting to have a life that's intellectually stimulating, if that's the things that you value, then go that direction, and build on it. And keep in mind that even though you hope your values stay going in the same direction, they will deviate in some, because you'll add more as you go on. But the point I'm trying to make is that you don't want to adopt others' values because you think they're better than yours. So you don't want to choose to go in a direction because somebody else wanted you to do that. That's what I'm trying to say. Because the last thing you want to do is get to Nick's age or my age and look back and go, oh, whose life did I live? Oh,
we're just youngsters.
Yeah, that's right. Well, but even in your 30s, because you spent 10 years doing what everybody else was doing, so you did it, but you weren't sure you wanted to do that, or what your parents wanted you to do. But I don't know.
I think
didn't quite fit your value set.
Yeah.
So then do a course correction. But I think it's important to value what you value when you go on. And the second thing is to in the journey, whether it be in the classes that you take or what you do in life, is to take some risks, get out of your comfort zone to do things. Whether it means meeting people that are a lot different than you, working with people that are a lot different than you. I can remember an event that I went to I think it was in Thailand, and it was a big women's science event, and there was a big table full of women from Africa, not my skin color by any means, and I didn't know anybody at that meeting, and I thought, God, I'd really like to get to know them, but I'm really different, and they were all from Nigeria, And so I took the risk and I sat down with them, and I just kind of listened to them and then became part of the conversation. And I thought they were going to be so different than me, but I found out all these women scientists, what they were talking about, beyond their science, was they just start talking about where they wanted to go shopping, where they all want to go shopping, after we got done with the meeting. And it was like, whoa, I can resonate with that. I certainly can resonate with that. So it just opened up a whole new world for me. I then started, traveling to Africa and meeting a lot of the other African women. So, but that was, for me, that was taking the risk to do something different. And the point is that if you're always doing the same thing over and over again, you really don't learn that much. You learn how to do it better and better and better and better. But when you take a risk and it works, whoa, your confidence really gets bolstered. So take a risk and try different things. And you're not going to fail, but when you fail, it's not a true failure if you learn something from it, right? That's with experiments too, right? If you learn something from it, that's how we experiment. And the third one is when you're trying to make a life decision that's really important to you, whether it be to go to graduate school or go to professional or take some kind of a job. And, it's really an important life decision. Don't do it when you're not feeling good about yourself, when you're feeling I'm the dumbest person on the planet, and so I'm going to go do this. Make that decision when you're at the top of your game, and however you get there, whether you run a marathon and finish it or whatever it is, make your decisions when you're there, because that then will say, oh, I'm smart enough to do this, I can do that too. And so you're more likely to take on something that's more challenging and it'll get you further rather than obsessing over the things that you're weak at. Obsess over the things that you're strong at. So those would be my three bits of
Excellent
advice.
points. I'm a little jealous. You're sitting outside, it appears.
No, actually, I'm sitting in a greenhouse that we have here. So,
okay.
So this is actually my office now here in Eugene, where I'm here for a week while I do a lot of West Coast trips.
It's about 30 degrees here, and we had snow today. So.
Oh, I know. I'm sorry. Actually, I was in Iowa last week, and it snowed there. So, okay, I get it, right?
Yeah. We're having a late spring for sure.
Yeah.
Oh, let's see. We have no more questions coming in.
Okay. Well, I want to say thanks to everybody for coming tonight, and Nick for the invitation. I'm really honored to be able to give this lectureship, and so delighted that DOE let me do it too. I wish you all the best, and whatever you do, and I can't tell you how special it is, Nick, to connect with you too after all these years, and at this wonderful institution that you're at. So I wish you all the best.
I have to say the honor is actually ours. It's been delightful, and catching up a little bit on what you've done and what you're doing. Always impressive and always fun. So hopefully when COVID's over, we'll have a chance to get together again in person. I think the last time I saw you was when you were getting the Priestley Medal, actually.
Oh.
So that's been a while.
That's been a while. But not as far as it could have been, right? Not as long ago as it could have been.
That's true. That's true.
That's right.
But anyway, I wish you the best, and I'm sure that the climate will benefit from having you in Washington. We're pulling for you to make that work.
Great. Well, thank you all, and good evening. Good evening to you.
Take care.
Bye-bye.
Bye-bye.